everyone. I'm Aruna Joseph, a research scholar from Bishopmore College, Mavelikara in Kerala in India. Today, I'm here to present my work on the topic, the tailoring the optical and dielectric properties of MnFe2O4 with the dysprosium substitution. And this is the introductory part of my work. And ferrites are a potential candidates among the materials due to their unique electrical and magnetic properties. They are classified into different structures based on their crystal structure. They are spinel, garnet, hexagonal, and orthoferrites. And the spinel ferrites are generally represented as MnFe2O4, where the M ions corresponds to the metal ions and Fe corresponds to the iron ions. And the spinel ferrites, based on the occupancy or distribution of these metal ions and Fe ions between the octahedral and tetrahedral sites, they are again classified into normal, inverse, and mixed spinel structure. And these spinel ferrites are unique candidates because of their high magnetic permeability, electrical resistance, chemical stability, which make them to enable to use in different applications such as spintronic, electronic devices, magnetic diagnosis, electrical generators. And among the spinel ferrites, manganese ferrite is an important candidate. Because of their strong magnetic behavior, high resistivity, low eddy losses, high coercive field, and high biocompatibility. Recently, it is found that the rare earth ion substitutions in the spinel structure of the spinel ferrites enhances its dielectrical and magnetic properties due to their larger size, unpaired F4 electrons, and spin orbit couplet. Here we choose dysprosium as the rare earth ion to tailor the electrical and magnetic properties of MnFe2O4. And to synthesize this pristine and dysprosium substituted MnFe2O4, we adopted Solskjaer autocombustion method, and for that, the corresponding precursors of metal nitrate, manganese nitrate, and iron nitrate were dissolved in distilled water, and dysprosium oxide were dissolved in citric acid. Nitric acid, and this mixture is again mixed with the citric acid, and ethylene glycol is added to the solution. The solution is then placed on a magnetic stirrer at 80 degrees Celsius. Then it is transferred to the hot plate, and until the solution gets boiled, ignited, and caught fire to get a spongy powder. After that, the powder is grinded using an agato motor, and it is sintered at 500 degrees Celsius for 5 hours. And the finally obtained powder is carried out for structural, morphological, optical, dielectrical, and magnetic study. And to study the crystal structure of pristine and dysprosium substituted manganese ferrite, Ritfield refined XRD analysis were carried out. From this, it is found that the characteristic peaks of the samples were corresponds to the cubic spinel structure of MnFe2O4 with the space group FD3M. And typically, metal ions occupy two sites in spinel ferrites. They are octahedral and tetrahedral sites. And from the Ritfield analysis, the occupancy of MnFe and Dy ions were retrieved, and it's tabulated in the table. From the table, it is found that the MnFe ions occupy both the tetrahedral and octahedral sites, which exhibits the mixed spinel structure of MnFe2O4. Also, from the table, it is found that with increasing Dy concentration and the ion occupancy decreases, which indicates the successful substitution of Dy ions in the Fe sites of MnFe2O4. Also, from the Ritfield analysis, it is found that the peaks, the major characteristic will shift to the right angle side, which indicates the decrease in the lattice parameter value. This is due to the transfer of Fe ions from the octahedral site to tetrahedral site. This is because the ion in the octahedral site has a smaller ionic radius than larger ionic radius than ion in the tetrahedral site. Due to the transfer of these Fe ions from the octahedral to tetrahedral site decreases the ionic radius of octahedral site, and which further reduces the lattice parameter value. And the transfer of Mn and Fe between the octahedral and tetrahedral site and the occupancy of Dy ions in the octahedral site induces strain in the MnFe2O4 lattice. And to study the strain, Fulder-Wagner method is adopted, and the equation and the relation is shown in the slide. And by plotting FWHM tan theta the whole square versus FWHM by tan theta sin theta, and using the linear fit, we can obtain the crystalline size and strain from the plot. And it is found that the crystalline size decreases with the device substitution. This is because of the increase in the induced strain in the MnFe2O4 lattice with the device substitution. And moving to the morphological analysis, the FSM images and the corresponding grain size distribution curve of the pristine and MnFe2O4 MnFe2O4 is shown here. From this, it is clear that the grains are distributed irregularly with the distinguishable grain boundaries, and also the grain size decreases with the dysprosium substitution, which is comparable to the crystalline size variation obtained from the AtC-AtG analysis. And this decrease in the grain size is due to the induced strain in the MnFe2O4 lattice, which inhibits the grain growth and which further reduces the grain size of the material. And to study the valence states of the Mn and Fe ions in MnFe2O4, the XP study were carried out. From this figure, it is clear that for device substituted MnFe2O4, 3 additional peaks corresponds to the device energies are found, which indicates the successful substitution of device in the MnFe2O4 lattice. And to study the valence state of Fe and Mn in MnFe2O4, the Fe2p3x2 and Mn2p3x2 spectra were deconvoluted. And the first figure shows the Fe2p3x2 spectra of MnFe2O4 and Dysprosium substituted MnFe2O4. 5 peaks located at 5 peaks were located, and which corresponds to the different valence states of Fe. And the lower binding energy located at 707 corresponds to the valence of Fe2 plus, and the other 4 peaks corresponds to the valence Fe3 plus valence states located in the octahedral and tetrahedral sites. And this also the mixed valence ratio of Fe2 plus bar Fe3 plus calculated, and which increases with the device substitution, which is further helpful to study the dielectric property of MnFe2O4. Similarly, the Mn2p3 spectra also deconvoluted and obtained 5 peaks, and the peak at higher energy correspond to the Mn4 plus valence state, and the other 4 peaks corresponds to the Mn2 plus valence state at the octahedral and tetrahedral sites. Also, the mixed valence ratio of Mn also calculated, and which also increases with the dysprosium substitution, which is also helpful to study the dielectric study, and which is in the upcoming slide. And also the electronic structure of the material were studied, and it is found that the reflectance spectrum, reflectance of the dysprosium substituted MnFe2O4 increases with the device substitution. This is due to the creation of localized states in between the valence and conduction band. And to study the electronic structure, the band gap of the material were calculated, and from the figure it is found that the material exhibit 2 linear regions, one at lower photon energy and the other at higher photon energy. The one at higher photon energy corresponds to the optical band gap, and the one at the lower photon energy corresponds to the defect band gap due to the localized states. And it is found that the band gap is lower for device substituted samples than the pristine one, and also the defect band gap increases with the device substitution, which is due to the creation of localized states in between the valence and conduction band. And to study the density of localized states, Arbok energy of the material are calculated using this relation, and by fitting the linear fit, we can obtain the Arbok energy value, which is the density of localized state, which also increases with the device substitution, which decreases the band gap of the material. Also, the density of this localized state also affects the concentration of carrier concentration in the material, and which was also calculated using this relation. And it is found that the carrier concentration is higher for device substituted samples than the pristine one. This is also helpful to analyze the dielectric study of the material. And moving to the dielectric part, to study the effect of dysprosium on the dielectric property of MnFe2O4, the dielectric measurements carried out with the frequency range 100 to 5 MHz at room temperature, and it is found that dielectric permittivity decreases with the increasing frequency. This is due to the associated with the Maxwell-Wagner polarization in accordance with the Gibbs phenological theory. And it is found that the MnFe2O4 has a dielectric permittivity of order 10 raised to 5, which is very much higher than the reported values of MnFe2O4. This is mainly due to the influence of several intrinsic parameters such as induced strain, availability of free charge carriers, grain-grain boundary effect, presence of multiple valence states of Fe ions, transfer of Fe ions and Mn between the octahedral and the tetrahedral sites. And it is also found that the dielectric permittivity of MnFe2O4 increases with the dysprosium substitution. This is due to the interfacial polarization due to the defect state concentration and the dipolar polarization occurred by the structural distortion due to induced strain. Also, already I have said in the optical study that the density of localized states increases with the device substitution. This increased localized states increases the trapping of charge carriers, which enhances the interfacial polarization. Also, from the AtC-AtG analysis, we found that the strain also increases with the device substitution. This strain distorted the structure and enhances the dipolar polarization. Also, from the XPS analysis, we found that the mixed valence ratio of Fe and Mn increases with the dysprosium substitution. This also enhances the dielectric permittivity of MnFe2O4 with the device substitution. And to study the relaxation mechanisms in pristine and disposal substitute MnFe2O4, the dielectric relaxation curve were fitted using HN relaxation model, and which is shown in the slide. And the perfect fitting of this model indicates the contribution of more than one ion to the dielectric relaxation process of MnFe2O4, that is Mn, Dy, and Fe ions. And also it is clear that found that relaxation time increases with the device substitution, which is due to the density of localized state, which traps the charge carriers, which enhances the relaxation process, and thereby the trapping charge carriers require more time to complete the relaxation process, which enhances the relaxation time. Also, the conductivity due to space charge carriers also increases with the device substitution, which is also due to the density of localized state, which trap more charge carriers, which enhances the conduction by space charge carriers. And finally, the Dysprosium substituted MnFe2O4 effect for the magnetic measurements were carried out, and it is found that the material exhibit a normal S-type curve, which corresponds to the superparamagnetic behavior with negligible resonance and coercivity. This is due to the small crystalline size that makes the particle to control the magnetic anisotropy. Also, the size of the synthesized nanoparticles are in the range of 13 to 8 nanometer, which is very much lower than the reported critical limit for a material to exhibit superparamagnetic behavior. And also it is found that the magnetization decreases with the dysprosium substitution. This is because this can be correlated to the fact that the rare earth ions particularly exhibit the magnetic moment due to their localized 4f states, and they are characterized by lower ordering temperatures. So as a result, the effect of rare earth ions in the Fe sites of MnFe2O4 seems to be similar to the substitution of a non-magnetic ion in the Fe sites of a spinel structure. Thus, the substitution of this rare earth ion creates a weaker dy-Fe interactions incomparable to the strong Fe-Fe interaction. This leads to a decrease in the saturation magnetization. And moving to the conclusory part, these are my conclusions from the work. The dysprosium substituted manganese ferrite were successfully synthesized using Soldier auto-combustion method, and the XRD analysis found that they exhibit a spinel cubic structure, and also the dielectric property enhances with the device substitution, and the magnetization decreases with the device substitution. Thank you all for your kind attention.
Thank you a lot for your reports. That's time for asking questions. So, does anyone have a question? Let me just start asking. The report is really huge. The study is so detailed, but maybe I missed why you selected dysprosium for substitution. What? It's so expensive element.
Because dysprosium is a larger ionic radii than iron, which enhances also it has contained multiple valence states, which enhances the properties of MnFe2O4.
I see. Do you have any alternatives?
What, sir?
Do you have any alternatives to dysprosium? Is it the only material of choice?
And yes, sir. We are trying for different rare earth ions, and one the dysprosium is one among this.
Okay.